Okay, so now we'll do the Diffie-Hellman key exchange problem. So you're given here um, that Alice is generating 15, Bob is generating 29, and the values of G and N are given 13 and 45. So you want to find what the secret key that they'll be agreeing with. So you have to do this modular exponentiation twice. First you have to compute G raised to A mod N. Then whatever you get on it, you have to compute G raised to A mod N, that whole thing raised to B mod N. Okay, so we'll do that now. So G raised to A mod N is 13 raised to 15 mod 45. So the exponent 15 is basically all ones, 4 ones. So we'll compute up to 8. So 13 raised to 1 mod 45 is 13. 13 square mod 45 is 13 to the 1 mod 45 times 13 to the 1 mod 45, which is 169 mod 45. Now, if you don't know how to calculate the reminders, let me show you. You want to calculate 169 mod 35, so it's 169 divided by mod 45. So divide by 45, so that's going to get you 3.755 and so on. So now get rid of the quotient, which is 3, so minus 3, so that gives you the fractional part. So multiply the fractional part by your divisor, which is 45, you get the remainder to be 34. Okay. So now 13 to the 4 mod 45 is 13 square mod 45 times 13 square mod 45. So 13 square mod 45 is 34 times 34 mod 45. So 34 times 34 is going to be this, divided by 45 is going to give you this. Now get rid of the quotient, minus 25, that is 0.68 and so on. So that multiplied by the divisor gives what we had, 34 times 34 divided by 45 minus 25 times 45, it's going to give you 31, the remainder. Now 13 raised to 8 mod 45 is 13 to the 4 mod 45 times 13 to the 4 mod 45, that is 31 times 31 mod 45. So that's going to give you something like this, minus 21 times 45, so that is 16. So 13 to the raised to 15 mod 45 is 13 raised to 8 times 13 raised to 4 times 13 square times 13 to the 1. So 13 to the 8 is 16 times 31 times 34 times 13. So 16 times 31 is going to be this, 496, divided by 45 minus 11 times 45 is going to give you this, times, so we found basically 16 times 31 mod 45 is 1, then that times 34 mod 45 is still 34, so 1 times 34 is 34, times 13 is 442, divided by 45 minus 9 times 45, that's going to be 37. So you have found 13 raised to 15 mod 45 is 37. So we send that to Bob, and Bob computes 37 raised to his B value 29 mod 45. So 37 raised to 1 mod 45 is 37. Of course 29 in binary is this, so we'll go until 16 and then put everything together. So 37 raised to 1 mod 45 is 37, 37 square mod 45 is 37 raised to 1 mod 45 times 37 raised to 1 mod 45. So essentially we are computing 37 times 37 divided by 45 minus 30 times 45, that is 19. So then 37 raised to 4 mod 45 is 37 square mod 45 times 37 square mod 45, which is 19 times 19 mod 45, which is going to be 19 times 19 is this, divided by 45 minus and this, so the fraction part times 45 is going to be 1. Then 37 raised to 8 mod 45 is 37 raised to 4 mod 45 times 37 raised to 4 mod 45, that is a 1 times 1 mod 45, which is a 1. 37 raised to 16 mod 45 is 37 raised to 8 mod 45 times 37 raised to 8 mod 45, so it's again 1 times 1 mod 45 is a 1. So 37 raised to 29 mod 45 is 37 raised to 16 times 37 raised to 8 times 37 raised to 4 times 37 raised to 1 mod 45. So it is 1 times 1 times 1 times 37 mod raised to 1 is 37, right? So the whole thing is now 37 mod 45, which is 37. When you divide a number by a larger number, the remainder is that number itself. So since 37 is less than mod 45, 37 mod 45 is 37 itself. Okay. All right. So now let's look at. So if I want you to answer on Needham Shorter protocol, you should make sure you remember each of those steps. But I would not probably ask you to draw it, the whole figure. I would give you something like this, and you need to fill up the missing things. For example, this could be the secret key that the initiator A and the KDC agreed upon, and you have to put KA here. And this would be something like encrypted with KA, but this is KS, the secret key that the KDC is trying to distribute to both A and B. So try to kind of understand each of those individual steps, and then you can write them. Okay. Similarly, for the public key authority thing, try to understand the whole thing, how each of those steps are executed, and then try to incorporate them. Okay. Fill up the missing things. Okay. Okay. So now let's go to module 3, which is on Bloom. It's all basically everything, right? Authentication mechanisms. Okay, so why is a Bloom filter guaranteed not to generate false negatives? A Bloom filter is guaranteed not to generate false negatives is because you're filling up the Bloom filter based on the hash values of the bad passwords or unacceptable passwords in your dictionary, right? So if you have so initially you fill up the Bloom filter with all those hash values, corresponding bits are set to 1. So when you test a particular word, if it's already in the dictionary of unacceptable or bad passwords, then the corresponding hash values, those bit positions in the Bloom filter would be set to 1. So there's no way you can have a word in the dictionary for which the bit positions of its corresponding hash values will not be set to 1. So if a word is in the dictionary, all the corresponding bits of its hash values in the Bloom filter would be set to 1. So there's no way you can have false negatives. But there could be false positives. Why? Because there could be some other words for which their hash values would have the corresponding bit position set to 1. Like we had that example. The word undertaker, when run through the two hash functions, will lead to bit positions 25 998 set to 1. Similarly, this word would lead to its bit positions 83 and 665 set to 1. So now our test password would get hash values like this. But if you look at the Bloom filter, the corresponding bit positions would have been set to 1 because of these two words. So this word will be classified as an unacceptable password because based on the Bloom filter contents. But doesn't mean that this is actually in the list of or need not be, right? As in this case, this test password is not one among these two words. So this is a case of false positive. Okay. The three forms of token-based authentication: the increasing order of complexity, rigor, and sophistication. You have them something like this. One is a traditional token where the user ID is kind of captured in the form of the barcode, and when somebody swipes the card, the user ID is sent to the server, and if the user ID is registered to the server, the person is let in, because just the scenario of possessing the card is considered as that you are the only person who is going to have that card. Okay. But of course, it's not secure, because if you lose the card, someone else also takes it and swipes the card, then that person also can get in. So that is the drawback of the traditional token based approach, or memory card based approach. Now, a little bit sophistication is after you swipe the card, you could be required to enter a PIN number. So again, for each user, you could set a PIN number at the time of registration, and if that PIN number is basically then sent by the card reader to the other side, and the other side can check, the server can check basically whether that PIN number is corresponding to that user. So then, if it matches, then the user can be let in. Of course, then it is possible the reader could be tampered to kind of send some special PIN numbers that are known to be registered at the server side and all these things, right? So this is a kind of better than the previous approach, okay, but not really sophisticated because the card is still kind of a dummy thing because you just swipe it and once you know the PIN number you can penetrate. So the last category is what is called a smart card, where you try to add some intelligence to the card or the token itself. So the card has a microprocessor and all the memory that can store some information and the protocols and all these things. So when a user swipes the card, and he may be entering a PIN number, but that PIN number is built into the card itself. Okay, so then the PIN number is validated by the card itself, so you cannot tamper it that easily. And then the card may do its own authentication with the server. So it's again a two-stage authentication: the user authenticating to the card, and then the card authenticating to the server. Or as we saw, the server could send some question, a challenge, and then the user would be required to participate in it by again entering a PIN number as part of the response calculation process, and then the token could send the response back to the server, which is further validated. So all these things require the token to be actively involved in the authentication process, whereas in the first two cases, the token is not actively involved. It's only the just the swiping or entering the PIN number. It's not really involving the token. Okay. All right. The two common vulnerabilities of password-based authentication and some countermeasures. So we saw that in the beginning. One common vulnerability is a dictionary attack, where an attacker could have a dictionary of well-known passwords or words that are used as passwords and the corresponding hash values. So that is what is actually called the rainbow table. And an attacker could basically then try to get access to the password file, and even though the password file may have the hash value of all the user passwords, he could then run each of those words in the rainbow table through a hashing algorithm and see whether any hash values match, and if there's a match, then that is a password for the corresponding user account. Then the other is common problem with password-based authentication is social engineering attacks, where attackers will try to trick the user's admin to reveal the password. As I said in class, you can probably email the admin by telling that you forgot your password, and you send that email from some other account, email, Yahoo or Hotmail, that has your name. Okay, but just by looking at that email address, someone should not believe easily that that comes from you. I can create an email address that has your name on it, right? So that's what is called a common social engineering attack, trying to through social practices, trying to influence the admin and try to extract or make them reveal the password. Okay, so some countermeasures are to the common countermeasure is someone tries to repeatedly log in and gets a password failure. You try to lock the account, and you could reset the password and email it to another email address or something. They would have given a secondary email address, or some way you can contact the real user and inform them that your password has been reset. Another countermeasure is to enforce users to choose passwords within a character set and reasonably longer enough so that it's very difficult for someone to really launch any attack. Okay, and also if you are not actively using the machine after you logged into your account, for example, you guys do the registration in POS, but after a while, if you're not using it, the system should automatically log you out. Don't let you to stay logged in. Okay, so these are some of the countermeasures.